Okay, it's time. Good morning, everyone. Welcome back to a brief break. So before we start, please don't forget that on Wednesday I gave a lecture, right? I taught and I made notes. I posted all the files like I usually do, right? So if you've not looked it up, check those videos as soon as possible because the content will be very, very important going forward, right? But before I continue from where I left off on Wednesday, do you have any questions for me before we start? Is there any issues, any concerns, any comments? Okay, so if there are no issues and no comments, then let's continue from where we left off the last time. So I'm sharing my screen. Please, if you can't see, do let me know, right? So we are on the chain rule 3.4, right? So on Wednesday, I explained, we started on Monday, right? But on Wednesday, I did a lot of examples and gave some further explanations, and we were at, there are still people coming in. Okay, let me know. Okay, so we were on this slide the last time. Yeah, on this one. So the last thing we're trying to do was to derive a kind of like a general rule for an exponential function. The only exponential function which we have the rule for is e to the x. So for now, we are just going to find a general rule for any, whenever we have a different constant, like not e, but rather say 2. What is the derivative of 2 to the x or 3 to the x or any number to the x, right? So that's the exponential rule that we're going to derive here. The rule about exponents, right? An exponential function. So let's start that on the whiteboard with a proof. So where's my stylus? Yeah, right here. Okay, so with a normal exponential function, by the way, I'm sharing my whiteboard. If you can't see the whiteboard, do let me know. So for the exponential function, right, we have b to the x, like so, right? It's b to the x, where b is usually said to be greater than 1. Right? So if you have this, how do you get a general rule for this? If you want to find a derivative, well, how are you going to get it? Well, one thing that we can do here is, remember that if you have b to the x, right? So recall, or note that if you have a, say, let me first erase this and use e rather. If you have e to the ln of, say, x, then it's just equal to x, right? If you have e to the ln of x, then it's equal to x, right? So using this property, we can rewrite what we have here, the b to the x, as what? E and then ln of what? B to the x, right? E ln of b to the x. In other words, when you take the exponent and you take the, so first take the log of something. When you take the log of something and you take the its exponent, right? If you take the natural log of something and you take its exponent, you get the same thing, right? You get the same thing. So if I have b to the x here, I can just take the log of that b to the x and take its exponent, and then kind of like the e and then the natural log here will cancel out, and it will still give me b to the x. So this is where I am now, right? So continuing with this, I see that for this part to note this rule, recall that if you have, remember that if you have, say, ln of x to the a, then it's just equal to a ln of x, right? I hope you remember this rule. So you can essentially just move the power in front to multiply the log, right? So that's what I did up here. So just considering ln of b to the x, I can just bring x in front of the ln of b, and then I have this. Well, now that I have this, let me just proceed and try and get the derivative. So y prime is just d over dx of what? E to the x ln of b, right? So this is where I am now. Okay, so now moving forward with this, the question is, how do I get this derivative? So I asked myself, do I have a direct derivative for this? No, we don't have any direct derivative for this. The closest we have is the derivative of e to the x, but this is not e to the x, it's e to some other function. But then looking at e to the x ln of b, you can think of this as a composite function, right? So this can be thought of as a composite function where the outer function is e to the x, and then the inner function is this, right? So that means we can employ the chain rule, right? So the chain rule, employing the chain rule, what do? we differentiate the outer function, right? In other words, differentiate the mother, right? Keep the baby inside, right? So you differentiate the outer function. What is the derivative of e to the x? It's just e to the x. But don't forget, you have to keep the baby inside, right? The baby in this case is the inner function, which is x ln of b. So just x ln of b times the derivative of what? The baby. So times differentiate the baby. What's the baby? X ln of b. So differentiate the inner function, x ln of b. Right? So moving forward with this proof, for this side, don't forget that ex ln of b is the same as the y. In other words, the same as the bx, b to the x, right? This b to the x is the same as ex ln of b, is the same thing, right? So that means for this one, for the y prime, this is what? B to the x. This ex ln of b is b to the x. Times, now we just have to do the derivative of this function. But looking at this function, what form is it taking? Well, first and foremost, you can see that ln of b is a constant. Don't forget the base here is supposed to be a constant, right? It doesn't depend on the x. So that means we can employ the constant multiple rule. So by the constant multiple rule, just pull the constant out and then times the derivative of what? Of x. So that will give us y prime, which is what? B to the x ln of b. And then dx over ds is just 1. So this is our final formula, right? So writing this well as a standard derivative, you have d dx of b to the x is just equal to what? B to the x ln of b. Now, do you remember in the past, in 3.1, we said that the derivative of an exponential function is always proportional to the function itself. If you remember, how we got the derivative of e to the x was, we said that e to the x, so let me write this. So recall that when we had f of x equal to this, we said that f prime is equal to b to the x and then f prime of 0. I hope you remember this way back. We showed this in 3.1. But we said that e is the case whereby the f prime of 0 is 1. That's how come we got the derivative of e to the x to be e to the x. So now this f prime of 0 that we're looking for is now has a precise definition. It's actually the log of what? The base. It's just the ln of the base. You see, this is what was the f prime of 0. So essentially, the reason why we are getting the derivative of e to the x to be equal to e to the x is because is technically this general rule. Repeat the same formula for an exponential function. Its derivative is proportional to the function itself. So repeat the same function and then multiply by what? The ln of the b, which is the f prime of 0. So the ln of what? What's the b here? The b here is the base, which is e. And what is ln of e? It's 1. That's how come you're getting e to the x. So the point I want to put across is this is a more general formula, right? This is the more general formula. So no matter what, if you memorize this, you will be able to get the derivative of e to the x. But I mean, no one even forgets e to the x in the first place. But you can link it with that and just remember that whenever you have a constant to an x, an exponential function, its derivative is what? Repeat the same thing, which is the constant to the x, times what? The natural log of the what? Of the base. That's all. Please, any questions on the proof? As I said, I'm not going to ask you to derive any proofs. This is the takeaway. This one is the takeaway. But then it's a good idea to see where they are coming from. And that's all. Please, any questions here? Okay. Anybody needs time? Okay, then let's go to the whiteboard. And then so the whiteboard, so this is just showing us the proof that I just did, right? So this is the takeaway. As I said, don't worry too much about the proof you don't understand, but try and see if you can comprehend this. It's kind of like good to know, right? But then this is the takeaway. If you don't see anything, at least you should know this one, right? And then now what that means is if you are doing the derivative of 2 to the x, this is an exponential function. So what do? Repeat the 2 to the x times what? The natural log of what? The base, which is 2. You see? That's how come we had an estimate of this in the past. It turns out that ln of 2 is approximately that number, right? It's just linking this with what we did in 3.1. But this is the actual rule, and that's all. Okay. Now, with this, let's go to example 10. So let's try this. I think this one is already given, right? So if you have g of x equal to 2 to the x, then j prime, so for a, j prime of x, you attach d over dx to 2 to the x. And then you ask yourself, do I have a standard derivative for 2 to the x? Well, now we do, right? Now we do. So the standard derivative is just 2 to the x ln of 2, and that's all. Done. Now let's look at the b. So we want h prime. So still attach d over ds to 5 to the s squared. And then ask yourself, do you have a standard direct derivative for this? Well, the closest we can get is 5 to the x, but this is not 5 to the x, this is 5 to the s squared. So it's as if the x has been replaced with some x squared. Do you see? So that means that this one is going to be the chain rule here, in a sense that the outer function will be what? Like the outer function is like 5 to the x, and then the inner function is what? Is s squared. This is the inner function. Right? The inner function is s squared. So what does the chain rule say? It says differentiate the outer function. So the derivative of, say, 5 to the x is 5 to the x ln of 5. Right? But we don't plug in s. You have to plug in the inner function. So that means it will be 5 to the s squared times the derivative of the inner function. Right? So moving on, we have 5 to the s squared, and then times ln of 5, and then times what? What's the derivative of s squared? That one is the power rule. So that would just be 2x. And that's our answer. Please, any questions here? That's the end of 3.4. Okay. Please, if you need more time here, let me know. Do let me know. Okay, no one needs time. Then let's proceed. Save. Continue. Come on. 3.5. Okay, so with 3.4 completed, let's move on to 3.5. And this is about implicit differentiation. Implicit differentiation. So for implicit differentiation, let's see what's about. Now, for all the functions we've met, right, you always see like y equal to, say, something like y equal to some function expressed in x, right? So like in function notation, I have, say, f of x equal to blah, 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 x, blah, blah, x, with x mixed in there, right? You have clearly x as your independent variable, right? So these are just two examples. So for the ones you've seen so far, you always see the dependent variable y to be on one side, and then the independent variable y to be on the other side, right? So you have an explicit solution for the y, right? The y can be expressed explicitly in terms of what? In terms of x. The same with this function. The y has been expressed explicitly in terms of x. So you have y equal to what? X sine x. Now, this is just saying that in general, for all the functions we've seen so far, it's like this. It's y equal to some explicit solution in terms of x. Now, it turns out that it's not always the case that you get an explicit solution for the y, right? Sometimes there are some equations whereby it's either difficult or impossible to rewrite y explicitly in terms of x, right? So let's look at these two functions. For these two, these two equations. For these two equations, well, for the first one and the second one, we can actually derive them. But as you can see, with this equation that you see here, we don't have an explicit solution for y directly. This one is an implicit, is an equation which is defined implicitly for y. It is implicit because the y is not like, does not have a solution directly. It's s squared plus y squared equal to 25. You don't have y equal to something in terms of x. You have y as a function inside there, mixed with some x's there, right? The same with the third and the second equation here, right? That one is s cubed plus y cubed equal to 6sy. That one is called the volume of Descartes. We talk about this later on, right? So the deal is, when we have an explicit solution for y in terms of x, then the derivative is just, we know that we just attach the differentiation operator, and then it will be in terms of x, and we do it using the normal rules. But the question is, what if you have an implicit, an equation which has y implicitly, y having an implicit relationship with x? Then what do you do? Well, one thing we can do is, if we can actually get the solution for y in terms of x, then we have a way to go, right? Even though it may be hard or difficult, we can still do it with the rules that we have, right? So for example, if you look at the s squared plus y squared equal to 25, this is an equation of a circle with center at the origin. So center is 0, 0, and then the radius is 5, right? So if you compute the y in terms of x, you start by subtracting s squared from both sides. Right? So you have 25 minus s squared. And then you get what? Y equal to, take the square root of both sides, you get plus or minus. Right? So 25 minus s squared. Right? So an explicit solution for y is defined by two separate functions. It is one, square root of 25 over s squared, or negative square root of 25 over s squared. But at least we have an explicit solution. So you'd be like, nah, we probably don't need implicit, right? We are okay. We are fine with this because we have an explicit. But what about something like this? For the s cubed plus y to the power 3 equal to 6sy, that one, it will be very difficult to have an explicit solution. In fact, they use a computer algebra to get the explicit solution. Right, very difficult to solve for y in terms of x. So they use a calculator, an algebraic calculator to do it, like a computer program for that, right? So this is just talking about the fact that for the first equation, we can solve for y. So that one, we can still say, well, I'll break this into two different functions and I'll apply my derivatives on them, right? No harm done. I'm still okay. I don't need implicit. But it gets tricky when you can't solve it, the volume of Descartes, right? This one. But before we get there, let's talk about this. How does it look like? So the general thing, the implicit equation that you have here, s squared plus y squared equal 25, is a circle, as I told you, with a center at the origin and then the radius is 5, right? If you break it up into an explicit solution for y, you get two functions. One is up here, the blue, and then one is down here, the green. So when it merged together, they give you the implicit equation, you see. Yeah, so the explicit solution for y gives you two separate functions. And then with that one, you can, if you are asked to find a derivative, you can just check for which part of the derivative it wants, whether it lies on this function or that function, and just apply it. So you don't necessarily need implicit, right? But as I was saying, it gets trickier when the function is a bit more difficult to obtain an explicit solution for y in terms of x. So for something like this, s cubed plus y cubed equals 6sy, it's difficult, right? They use a computer algebra program to get this. But similar to what we had for the graph of the implicit equation of s squared plus y squared equal to 25 being separated into two, you have a similar one for the volume of Descartes. So for this general graph, if you use the algebra calculator to solve it, it's very, very long, right? The solution is very long. That's why they didn't even write it like they did for this one, right? They didn't even write it. They just said the graph will look like this, right? So the first piece will look like this, the second part will look like this, and then the third part will look like this. When you join all of these, you get the volume of Descartes graph that you see here, right? Okay, please, are you okay? So far, are you getting the idea? So the deal is, if we were able to get an explicit solution for y in terms of x for all functions, then we don't need implicit. But as you can see, it could be very, very difficult or almost very complicated or even impossible to do it for some of them, right? So with that one, the good news is you always have implicit differentiation to help you out, right? You can always use implicit differentiation if you have an implicit equation. That is, the y has not been solved for in terms of x. You can use implicit differentiation. And that's all. Okay, so now how do we employ the implicit differentiation? Now, for implicit differentiation, all that you have to do is just note that, so looking at this, remember that the volume of Descartes is given by s cubed, y cubed equal to what? 6xy. The thing is, remember that, first and foremost, the y that we are trying to solve for in terms of x is some function of x. The y is some function of x. So that means technically we can just replace this y with some function of x. We don't know the exact form because we don't have an explicit solution for y. But we know that if we were able to express it explicitly, then it would be some function of x. So I can just replace the y with f of x. That's cubed. And then that's what 6x and then f of x. I can do this. Okay. Now, if I do this, let's see how the implicit differentiation is going to work, right? Let's see how the implicit. So if you understand this piece, I'm going to talk about how the implicit differentiation is going to work. Okay. So now all that we're going to do is we are just going to differentiate both sides of the equation. So essentially just attach d over dx to both sides, and then everything will follow through. You use that idea and then the chain rule, and then you will be able to do the implicit differentiation. So implicit differentiation it's not a lot new. It's just more like the chain rule, kind of. Now you see what I mean by that shortly. So let's look at the first example. So for the first example, it says if x squared plus y squared equal 25, find dy over dx. Now for this first example, I'm going to use like an explicit solution, get the derivatives, and then use the implicit differentiation. And then you'll be able to like compare and contrast, see the difference. Well, as you know, if we don't have an explicit solution, we can't solve for it. If it's impossible, then we can't even use the first approach in the first place. But if implicit differentiation is always there to make your life easier. So let's look at the first example. I'm going to do this on the whiteboard since the solution is already on there. So this 3.5, example 1. Okay, so we have x squared plus y squared equal to 25. And you have to find dy over dx. So if I have not already done implicit, what I'll do is, let me say approach 1. Please, you won't be using approach 1, right? I'm just showing you so that you can understand why we do the implicit, right? The approach 1, I'm going to solve for y, and then afterwards I will do the usual dy over dx. So for this one, what do you do? Okay, I'll say, okay, now I don't have y solve for, but I can kind of like do something with this. I can solve for y, right? So I have subtract s squared from both sides. And then I have y equal to like plus or minus square root of 25 over minus s squared. Oh, nice. Now we have an explicit solution for y in terms of x. So if I want dy over dx, I just do dy over dx is equal to what? So the plus or minus can come out, and then d over dx of, maybe let me put this inside first, and then explain that the constant multiple rule takes effect. So attach the differentiation operator to this, right? And then you have dy over dx equal to what? So for this one, the plus or minus can come out by the constant multiple rule. And then you do the derivative of what? You have 25 minus s squared all to the power half. Okay, now looking at this, what do you say? Well, for this one, there's no direct derivative, but I can see that this is a composite function where my inner function is this function. And then my outer function is some power function, right? So using the the chain rule idea, what do? Differentiate the outer function. So the derivative of the outer function will be bring the half in front, plug in the inner function, subtract 1 from the power because it's a power rule, and then times the derivative of the inner function. So that's 25 minus s squared. Right? Please, are you okay up to this point? Any questions on anything? Okay, so the derivative is just going to be plus or minus 1 over 2, and then 25 minus s squared to the negative 1/2. And then for this one, what do? Well, this is the difference rule, right? The derivative of 25 is 0 since it's a constant. And then I have minus the derivative of s squared is what? Minus 2x. Right? So the derivative I'm getting here is in 2 parts. There's one part which is plus, and that will go with the positive square root of 25 minus s squared. And there's another part which is minus, and that will go with what? That will be the derivative of the negative square root of 25 minus s squared. So there are 2 pieces of this derivative. That's why you see the plus or minus here, right? So that'll be our final kind of derivative in 2 parts, right? Okay, but as I said, it's not always the idea that you get an easy solution for y. So how do we do the implicit, which is the new idea here? How do we do the implicit? For that, I'll have to move on to the next slide. So do let me know if you need more time. Okay, so we say, okay, now for the implicit, this is the approach 2. Implicit differentiation. So for implicit differentiation, we have s squared plus y squared equal to 25. So this is what you're going to do. The first thing you have to do is just do d over dx of what? Of both sides. Because you're asked to find what dy dx, you're asked to find what dy dx. So if you're asked to find dy over dx, you just choose to do the d over ds of both sides of the equation, right? You are taking the d over ds from here, right? So d over ds from here. So just do d over ds of both sides. So I have d over ds of x squared plus y squared equal to what? D over dx of what? 25. Now the derivative of a sum is the sum of the derivatives. So for the first piece, for the left-hand side of the equal to, you have d over dx of what? Of x squared plus d over dx of what? Of y squared equal to. Now for this side, we have d over dx of 25 and the derivative of a constant is 0. So we have this. Now, this d over dx of x squared is the usual power rule that we've met all along, right? So d over dx of x squared is what? It's just 2x. Now, the main thing here is that we have to think about is this thing. This is weird in a sense that we've never seen a case whereby we have the dependent variable up here and then the independent variable down here. Always it's like if we are differentiating with respect to x, we have the expression in terms of x up here. But this case is different. There's y here and there's x here. That means the normal rules won't work. So what do we do? Well, as I said, for implicit differentiation, always put it in the back of your mind that the y is a function of x. It's a function of x, right? In this context, it's a function of x. So if y is a function of x, so let me just sidetrack here so that after we master this out, you guys can help me put this here. So suppose I have like d of y cubed dx. Now, as I said, with implicit, remember that y is some function of x. That means I can write this as what? D over dx of what? A function of x all cubed. Now, if it's some function of x all cubed, then how can we differentiate this? Now, the x and the x in here match, right? So if you're going to differentiate it, then it's going to become what? A composition, where the f of x is an inner function and then the 3 is an outer function. You see? So since it's a composite function, then I can employ the chain rule. So by the chain rule, if I'm differentiating something like this, to be differentiate the outer function, plug in the inner function, then 3 minus 1 times the derivative of the inner, right? So the derivative of what? F of x. I should be using the red. Yeah, so that means this simplifies to what? 3 and then f of x all squared, and then times what? What's d over ds of f of x? It's just f prime. But the question here is in y. So let me bring back the y in there. Don't forget that y is the same as f of x. So that means this becomes what? 3y squared. And then what's f prime? dy over dx. So that's a sidetrack. I think I see something in the chat. Give me a sec. Yeah, I intentionally did the y cube. I intentionally did the y cube so that you guys can help me with the y squared. Yeah. So that one I was just explaining for the y cube, yeah, in general, right? So that you understand that piece. So whenever you see y in there, remember that it's a function of x, right? And then you can employ the chain rule or the product rule or whatever rule that needs to be applied at that point, and then you get it. So it's nothing new. It's just the chain rule or the product rule or something. Just note that the y is some function of x if it's an implicit equation, right? So with that said, with this point put across. Now on an exam, you don't have to do all of this, right? You can just jump from dy cube over dx straight to 3y squared dy over dx. So if directly from here we knew that y is some function of x, then we know, okay, chain rule. So what do I do? To be differentiate the outer function. So that'll be 3y squared times the derivative of the inner function. So that'll be 3y squared dy over dx. You see? So now with that said, let's go back to the question. So with this one, we have 2s dy squared over dx equal to 0. So the question is, can anyone please help me with this? What do you think the dy squared over dx is going to be? What do you think? Based on what we just discussed, what do you think? Y is some function of x. So what do you think d over ds of y squared is going to be? Y is some function of x. Anybody? Okay, so I have 2 f of x. Thank you. Keep trying. You're close. Minus 2s close still. Keep trying. Yes, you're very close. Wait, okay. But guys, if this works out, please, right, if it's possible, try and see if you can share with everyone in the meeting so that if someone wants to second, it's easier and someone can see like what's happening. It's kind of like in a classroom setting where you just raise your hand and you say the answer or something. Okay, thank you. Yeah. So yeah, you guys have been giving very nice answers. Yeah, that's true. Thank you so much for your input. The answer is going to be what? Well, let's look at this expression we have here. We are doing d over ds of y squared, but think of y as some function of x. So that means some function of x to the squared. So by the chain rule, what do? Differentiate the outer function. So that'd be 2. Plug in the inner function, y, 2 minus 1, times the derivative of the inner function. So dy over dx equal to 0. So you guys were right for the 2y dy over dx. Please, are you okay with this? Okay. Anybody needs time here? Okay, so that means moving on, I have something like 2x. Oh, I have something like 2x plus what? For the 2y, 2 minus 1, that's just going to be 2y and then dy dx. So plus 2y dy over dx and then equal to 1. Is that it? No, equal to 0, right? Equal to 0. Yeah, equal to 0. Now, when you get to this part, you solve for dy dx. You solve for dy over dx. So you solve for dy over dx so that you get what? What the question asked for, which is dy over dx. So that means dy over dx will just be, first, I can subtract 2x from both sides. So that will just be 0 minus 2x, that's minus 2x. And then when I get here, since I'm solving for dy over dx, I'll have to divide both sides by 2y. Right, so that'll give me dy over dx equal to what? The 2's will cancel, that reduces to negative x over y. And that's implicit differentiation. Right? You see? Yeah, so you didn't even have to go through the solution. You just the solution for y in terms of x. You can just use implicit and then you have this. But please note this. One important property you see here is the y is mixed inside the x, right? With the derivative. With all that we've seen so far, always when we got the derivative, it was just some function expressed in x. But because you're doing implicit, you likely see the x and y's mixed in there, right? And that's no problem because we don't have an explicit solution for y. So it tends to come out as what? As part of the solution for the derivative. Please, are you okay? Yeah. And you see, this process was simpler than what we did for the solving. This first approach, you have to solve for y before you do it. And as I said, it's sometimes even impossible to solve for y in terms of x. So sometimes your only option is implicit. But even when you have more options, right? Even if you can use the approach 1, the implicit is always the best approach when you have an implicit equation, right? Because that one is faster. You don't have to solve for y in terms of x before you get a derivative. Okay, so with this said, please, do you have any questions here? Okay, let me stretch. Okay, anybody needs time on this? Okay, so that's the A. I'm sharing the PowerPoint now. Now, the second part says, find an equation of the tangent to the circle, s squared plus y squared equal to 25 at the point 3, 4. Now, I'll show you, the slide has the 2 ways of solving this, right? Since we're able to get a derivative by solving explicitly for y in A, you use that approach and then you use the implicit differentiation. But I'm going to solve the implicit differentiation on a whiteboard and then give you the chance to see how we would have done it if we had an explicit solution for y, right? So let's do the implicit. So part B, how do you get the equation of the tangent line for implicit differentiation? So B says, so we need equation of tangent at 3, 4. Now, the idea works in the same way with just a little bit of change. The only difference is, unlike the previous cases whereby we were plugging in only the s coordinate, with implicit differentiation, as I told you earlier on, is usually the case that the y coordinate will be part of the solution. So that means for this one, if you're trying to find the slope of the tangent, you end up using the x coordinate and then the y coordinate. So first, we need the slope. So it's the same thing, right? We need the slope. We have the point. The point is 3, 4. the slope of the tangent line. Let's call it m. And that means m is equal to what? It's just the derivative evaluated at what? At the point. Right? It's the derivative evaluated at the point. So the slope in this case will be what? It's negative x over y. So in this case, our x is 3, and then our y is 4. So it should just be negative 3 over 4. So that's our slope. Now that we have the slope and we have the point is 3,4, we can get the equation of the tangent line. So that's y minus y1 equal to the slope and then x minus x1. So this is it. And that's all. So the only tweak or the only change is that this time the y will be involved when you are finding the equation of the tangent, the slope of the tangent line, right? Because for implicit differentiation, the y is sometimes part of the solution for the derivative. Yeah, please, any questions here? Are you okay? Okay. Anybody needs time here still? Okay, then let's move on. So now, the first part is just showing us the implicit differentiation that we did. And then the fact that if you differentiate y squared, it's just what? You use the chain rule, right? In this case, you use the chain rule. Don't forget that the y is some function of x. So by the chain rule, differentiate the outer, so that'll be 2y, because you are plugging in the inner function, times the derivative of the inner function, which is y. And then you put that in there, solve for dy over dx. And then you have this, and that's your solution. Now, if you're trying to find the equation of the tangent at the point 3, 4, remember that 3 is your x coordinate, 4 is your y coordinate. You have to put them here because the x and the y are in there. So you get negative 3 over 4 is your slope, and then you can get the equation of the tangent. Now it's just going to show us the other solution, which was because we had an explicit solution in this case, right? In this case, we're able to solve for y to get 2 separate functions, right? Well, okay, so this is the first one. Now, this is the first one, and then the other one was negative square root of 25 over s squared. But then the point lies what? On 3,4. So remember that when we split the s squared plus s squared plus y squared equal to 25, you got one part, which was this, which represents the square root of 25 minus s squared. And then the other part was like so, which represented the negative square root of 25 minus s squared. I hope you remember, right? Way back here. Like this one. Yeah, this is what I'm talking about. These two. When we split this up, we got these two. So for if you want to use when you have an explicit solution, right? That means you just have to check where this point lies. The 3,4. It lies on the top one. It lies here on this one, on the top one here. The square root of 25 minus s squared, right? It lies on the upper one. So that means you're using this function. So if you know that you're using this function, then just check its corresponding derivative. Its derivative, as we obtained earlier on, is this. So now that you have the derivative, you can just plug in the point because you have an explicit solution, right? This time you just be using only the x because the point is 3,4. You just be using the x. For implicit, you're using the 3 and the 4. But when you have an explicit, you just be using the x. So you see, if you plug in 3, you get the same answer, negative 3 over 4 as your slope, right? And then you cannot get the equation, the same equation, same thing. But as I said, you won't be doing this because for implicit, you usually won't have an explicit solution for x. Okay. Please, any questions on this? I hope this makes sense. Okay, then let's go here. Now let's look at the volume of Descartes. Now that we understand what is happening here, right, with the implicit, let's try and work on the volume of Descartes and see if we can get it. So similar question, right? So A, find y prime if s cubed plus y cubed equals 6sy. So what do I do? If I want y prime is just dy over dx, right? So we have to find dy over dx. So what do I do? Let me probably like separate this into two. Okay, so the first thing I'll do is note that I've attached the d over dx to the y. So just do d over dx of both sides. So I have s cubed plus y cubed equal to what? D over dx of what? 6sy. And then for the left-hand side, this is a sum rule. So I'll just do d over dx of s cubed plus what? D over dx of what? Of y cubed equal to, for this side, is 6sy. But as I said, with implicit, always remember that the y is some function of x. Now, if y is some function of x, then that means for 6x times y and times the y, I can consider that to be what? A product of functions. This is a product of 6x and then y. So what happens there? I can use the product rule. So by the product rule is 6x times what? The derivative of the second, which will be dy over dx, plus what? The second, which is y, times the derivative of what? 6x. These are okay. So it's not always the case that you use the chain rule. It depends. Just think of the y as some function of x and then use the rule accordingly, right? The rule that applies accordingly. So in this case, for the s cube, the derivative of s cube with respect to x, we see this one is d over ds of s cube. So that one, no issues. It's just going to be 3s squared. Or, come to think of it, let me tell you about this. Technically, we have been doing implicit differentiation all along. Because if you're doing the derivative of s cube, what are you doing? Well, if you think about doing implicit differentiation, then the inner function is x. So if you do the derivative of s cube, think of the cube as some outer function. So that 3, plug in the inner function squared times the derivative of the inner function. But it turns out that all along, it's always giving us the s over ds, which is always 1. That's why we don't even bother bringing that piece. You see? So if this also works for you, you can also do this, right? You can also do this if this works. So we've been doing implicit all along. But it was kind of like hidden in there. So that's why we have this. If you do dx over dx, it's still 1, right? So that one still gives you the same thing. Now for this side, can anyone please help me? Oh, we did this already. I didn't see this coming. I wouldn't have done the same thing up there. So that one is over still. You guys want to give me an answer? What is the answer to this? Please try and see if you don't look and you can get the answer. What's the derivative of this? You're doing d over ds of y cube. What is that? Anybody? So yeah, anybody? What do you think? Okay, yeah, perfect, thank you. It's going to be 3y squared, perfect. dy over dx, perfect. Thank you very much. And then for this side, it's still 6x. dy over dx, you can't simplify that one. It's just dy over dx. And then for this side, the derivative of 6x is 6. So that's just 6y. And then after this step, what do? You solve for what? dy over dx. Let me see if I have some room on the next layer. Oh, I don't have room, so I have to create it. Okay, so now let's solve for dy over dx. So for dy over ds, we have to group like terms. I see a dy over ds term here, and I see another dy over ds term here. So I need to join them on one side, right? And then I have to subtract the 3s squared. So in the long run, I'm having 3y squared, and then dy over dx, and then minus 6x dy over dx equal to what? 6y minus 3s squared, right? And then when I get here, don't forget that we are trying to solve for dy over dx. I see the dy over dx here and the dy over dx here. So I can factor that out and have dy over dx times what? 3y squared minus 6x. Then equal to what? 6y minus 3x squared. And then when I get here, I'm trying to solve for dy over dx. So I'll just divide both sides by 3y squared minus 6x over 3y squared minus 6x. And that will finally give me dy over dx equal to what? 6y minus 3x squared over 3y squared minus 6x. Right. Yeah, you can simplify it if you want, but the web assignment will accept this. I will also accept this. I need to create a new, yeah, so that I can work this stuff here. Okay. All done. Okay, so now please, do you need time on this? Do you have any questions here? Okay, so that's this derivative. Now, the part B says find the tangent to the following with Descartes at what? 3, 3, right? So at 3, 3. So at 3, 3, 3, 3, we need the slope. Don't forget, we need a slope, right? So the slope will be odd. The derivative evaluated at this point. So the slope will be 6. Don't forget, this is my x, this is my y. So it will be 6, 3 minus 3, 3 squared over what? 3 3 squared. We are lucky here because the x and y are all 3. And then minus 6. So we don't have to change numbers here. Like so, right? We evaluated the derivative at what? At that point. And then you find this. So that'll be 6 times 3. Oh, now I wish I can cancel out stuff. So let me cancel. So I can factor out 3 here. I have 2. Okay, I have 6. And then minus 9. I could have even factored more. Maybe 6, no, 9. Okay, that's 3. Let me just leave this. And then I have 9 here. And then for the denominator, I can factor out a 3. And then I have what's left here. This is 9. And then minus 6. Okay, so that'll give me m equal to the 3 will cancel out. And since this is like the inverse, so that'll give me -1. Right, so because it's -3 and this positive 3. Yeah, that's -1. Now I have the slope to be -1 and I have the point to be 3, 3. So I can get my equation of the tangent line as y minus what? 3 equal to -1 x minus 3. And that's my equation. Please, are you okay here? Any questions? Anybody needs time here? Okay. Anybody needs time? Okay, then let's come here. So more examples. So let's find y prime if this is given. So what do? Well, we are doing, let me create some room here. So y prime is what? Y prime is dy over dx. So we just do d over dx of both sides. So we do d over dx of what? Sine of x plus y. And then equal to what? D over dx of y squared cosine of x. And then coming here, I say, okay, now let me get this derivative. But this one, the derivative of sine of x plus y, we don't have a standard derivative for sine of x plus y. We have for sine of x, but not for sine of x plus y. So what do? Well, I can see sine of x plus y to be a composite function, where the outer function is sine, and then x plus y is my inner. Right? So what do? Chain rule, right? So chain rule says differentiate the outer function. So the derivative of sine is cosine. Plug in the inner function times the derivative of the inner function equal to what? Now for this side too, don't forget that the y is some function of x, right? Some function of x squared times cosine of x is just a product of functions. So I employ the product rule. So by the product rule, leave the first one alone, multiply by the derivative of the second. And then plus what? Leave the second function alone, multiply by the derivative of the first. Okay. Now moving on, let's try and get the derivative. For this first one, we have cosine of what? Of x plus y. And then for this derivative, we have to do the sum rule, right? So the derivative of x is 1. The derivative of y, which is equal to s, is just dy over dx. Like so. Please, any questions up to this point? Are you okay? I hope it's not too messy, right? And if you need more help too, please seek help, right, as soon as possible. I'll be more than happy to schedule time and do more examples with you if that works. Okay, so if you're okay, then let's continue. Now, for this side, for the right-hand side, the derivative of cosine is negative sine. So you have negative y squared sine of x. And then plus, for the second piece down here, you have cosine of x. But the derivative of y squared, it will just be chain rule, right? So that'll be your times what? 2y dy over dx. So in the long run, I have something like cosine of xy, s plus y, sorry, s plus y. And then plus what? Cosine of s plus y. I'm distributing the cosine of s plus y. So cosine of s plus y dy over dx equal to what? So that's negative y squared sine of x plus 2y cosine of x dy over dx. But then I see dy over dx term here and dy over dx term here. So I can combine like terms. So I have cosine of what? S plus y minus 2y cosine of x all dy over dx equal to, and then I have minus y squared sine of x and then minus cosine of x plus y. dividing both sides by the coefficient of dy over dx, which is this, I get dy over dx equal to negative y squared sine of x minus cosine of x plus y. I think this is the last example because it's 49. It's almost time. And then all over cosine of x plus y minus 2y cosine of x. And that's my answer. I think there's the last example I'll do. Yeah, but please do let me know if you have any questions. Any part of this you don't understand. And feel free to reach out if you don't understand anything. You can work more examples. Yeah. So that's it. If you don't have any questions, that's it for today. Thank you for your time. And then, yeah, all the best. Have a nice weekend.
Thank you.
You're welcome. You are welcome. Same to you, Megan.